Okay. I appreciate you being here. My name is Kevin Reil. I am the Rubin Observatory scientist. I work at SLAC, but I haven't seen SLAC in a few years. But I'm going next week. It's very exciting. I'm going to kind of walk you through what I think are the most important things in all of Rubin for the next year. I know that's pretty arrogant. I know. I'm just trying to get us to first photon. That's all I'm trying to do. Some people are interested in photons. And more importantly, I'm going to use the word you many times. And so if you're wondering who you is, it's you. Before I get started, I just want to show this picture. This is from, I think, yesterday. This is our team in Chile working hard while we've been having a great old time here in Tucson. And I am very thankful for the team that's still going in Chile on the mountain, doing all the things that we need to do to stay on schedule. And this month looks fantastic. Everything's lined up. Everything's going to go perfect. September looks a little trickier. We'll talk about it. That's Miguel. He's from Spain. He helped build the telescope and then he stayed with us. It's awesome. So my job, portion of my job, I'm the system integration and test scientist. My job, as I envision it, is to get us from now until first photon. And then I tell people I'm going to disappear. It's probably not true. And so really, I love to tell you that I think we're less than a year away from first photon. Jelko gave you dates that are way later than I think, by like at least 4 days. But I think something before next year, this time, I think we will have photons coming through our system. And Michael, they're going to be out of focus. I'll fix it. I don't want to talk about it until I fix it. So we just had a session about information sharing. I don't want people telling them it's not fixed yet. So that's exciting. This is our block diagram of all the stuff ahead of us. I can't read it. On the top, there's the dome. I don't want to talk about it. Next down, oh, because it's going really well. No, really, they're staying out of the way. They're getting stuff done. They have not slowed me down at all. Love it. There's some bumps coming in the road on that. The calibration system, fantastic team working on it. I'm not going to talk about it. It's going to show up on the mountain. It's going to be awesome. TMA verification, I'll talk about that. M1M3, M2, commissioning ComCam, refrigeration pathfinder, LST Cam. I'll talk about all of those. And then Oxtel, what a workhorse. I've considered it part of operations for a long time, but it's not officially. We're still working on it. And it's been useful for so very many different things. This is the block diagram I made yesterday, which I hope that you can at least kind of read. The top row in red is M1M3 work. That's mirror 1, mirror 3. Green is mirror 2. We have a 3-mirror system, so that's all 3 mirrors. Followed by ComCam. I see you taking that picture. ComCam is on the telescope now. ComCam, I think most of you know, over the last year, we discovered we'll never see the sky. And that's because right down here, you see the LST Cam is on the telescope before the last mirror. And that's a good thing. So LST Cam is the last thing I'm going to talk about. A couple of things the main things that changed last year, we had a couple of schedule workshops. One of them is, I think you all know that we have a new pumped coolant system for the camera that involves some camera cable wrap work that we need to squeeze in. And not everything goes perfect on the mountain. And so while I think things have gone pretty excellent for the last many months, our dynamic testing did not finish exactly on the day we planned. Turns out some of the things that we do are hard, and we'll get there soon. And so we've split the dynamic testing between now and into September and October, and we'll be getting back to that soon. And so I'm going to kind of walk you through just the timetable of the things that are happening on the mountain. For those of you taking pictures of my slides, these boxes are accurate within a month. No more accurate. No, they're pretty good. but don't hold me to this. Last year at this time, this is what the system looked like. There's a great big yellow cross at the bottom. That is the Mirror-1, Mirror-3 surrogate mass. Up there at the top, you can see the Mirror-2 in white, Mirror-2 surrogate mass. And then in yellow in the center, that was the LST camera surrogate mass. And the telescope wasn't done yet. And they were just getting to starting the software testing. And what we always want when a vendor delivers to us is for everything to just work perfectly on day one. That didn't happen, but we plowed through and it's working. Working even well on occasion. This is a couple of pictures of the commissioning camera. I think some of you know this from previous PCWs. That's the commissioning camera being mounted onto the rotator. That is the mechanical interface to the telescope system. In the back of that is all of the utilities for the camera. The commissioning camera has all the same utility connections. We verified not just those mechanical interfaces, but the procedure to install a camera onto a rotator, which it turns out we're going to do again with the Reil camera soon. And then on the top right, in the right-hand side, that is the commissioning camera being installed on the telescope. Again, that's a critical lift. That's a lift that has to go perfectly. That is a lift of inserting in between the glass of M2 a camera that's very long with clearances that are not gigantic. And I think I kept in here a video. So this video is time-lapse sped up. This is 10 hours on the mountain. And what I really want you to pay attention to is how straight this camera goes in. Our mechanical team, Freddie Munoz, running things on the upper right there. A couple of places when it got really tight, you'll see that we stopped and backed out a little and made it perfect. And then went ahead and installed it. This is 10 hours sped up to 60 seconds. But you know, this is one of those days that you both dread and love. It's hard. A lift like this, an integration like this is not easy. It takes really, really fantastic people. As it turns out, we have those people. I don't know how many of you were able to visit the summit, you know, before the observatory was built, or more importantly for this slide, before we started putting stuff on level 3. Level 3 is the size of a football field. And it's just a gigantic empty space. And then you say, oh, I need a coating chamber that can coat an 8-meter mirror. And now some of your space is gone. And I need an actual 8-meter mirror. And now more of your space is gone. In this picture, that's the surrogate. And you remember the picture before, we saw a great big yellow cross that was the surrogate for the M1M3, just a mass surrogate. Well, it turns out that to put this M1M3 cell plus surrogate onto the telescope, you have to take this M1M3 surrogate off. And they can't just slip past one another. So you have to do things like, okay, we'll bring it out onto level 3, then we'll back in a truck, and then we'll take it out of the level 3, and then we'll roll the other one by, and then we'll back the truck back in again. And then it happens, and it's just perfect. But it takes a lot of people thinking about how to solve problems like that. And it really, I can't be more proud of the team on the mountain getting stuff like this done. This is that big yellow surrogate. This is the Pflow Lift. For those of you who don't know, there's a lift, not an elevator. You're not allowed to be on it when it's moving. Pflow Lift will take things from the 3rd level of the observatory. It can stop on the 5th level. It stops on the 8th level. But the roof of the observatory is on the 7th level. And so to get to the 8th level, you have to lift the roof off the entire observatory. And you have fantastic views. And this is the surrogate coming off of the telescope. And of course, now, if you don't lower this again, you can't rotate the dome because it'll hit the roof that just got lifted up. So this is the M1M3 surrogate coming off the telescope. This is the telescope with no M1M3 at all. That I hope you can tell that that's a little top heavy. And this is with the actual hardware in place. And this is about April of last year. We started the M1M3 cell testing. And it was going fantastically well. We did something called quasi-static tests. As you take the telescope down in elevation, can you correct for the gravitational forces? Yes, we can. Somebody decided along the way of this project to make a telescope that moves really, really fast. That's what we do. Turns out there's some forces involved in that you have to counteract on the mirror, on the glass to keep it safe. And you can't practice that until you put it on the telescope. And that's the dynamic testing that we split into two and are going to finish next month. All right. So looking forward, we are going to work on the dynamic tests. Essentially, that just means, can we move the telescope at full speed and move all the force actuators inside of the mirror cell to keep the glass safe? No glass on there yet. That's why we practice. And really fantastic team working on that. And I apologize, this is a slide from the JSR where I identified a risk that you don't need to know about. And so going forward, it looks something like this. We are today removing the commissioning camera. That video I showed you of the camera going in, we're doing that in reverse today. In order, you have to take the camera off to take the M2 mirror surrogate white off the telescope, because we're going to put the mirror to cell with just a surrogate mirror onto the telescope in a couple of weeks. And then we're going to put the commissioning camera back on. There's a bunch of other details in there, some work to be done on the camera cable wrap, thermal control system, stuff like that. We have about a month's worth of work with the system taken apart. But at the end, in the middle of September, we will have a telescope with mirror 1, mirror 3 cell on it, surrogate mass, the mirror 2 cell on it, surrogate mass, the commissioning camera on it, which if you don't love it is a surrogate mass, but it does a lot more than just that. It's a 144 megapixel astronomical camera. It's really quite fantastic. So we'll have the entire system on sky, except for the mirror part. And we can test that entire system and confirm well in advance of actually going into first photon that the whole system works. So that is September and October. November, cameras coming to the mountain. That's pretty exciting. And we need to get the camera into the white room and out of the way, because as you saw before on level 3, when the M1M3 work is happening, there's no room for anything. So the camera arrives, we get it into the clean room, all of the auxiliary equipment into the clean room, hook it up to get it cold. And now the M1M3 coating starts with surrogate coming off, the glass going on. Obviously, that's a really critical lift. Sometime in the December timeframe. And then LST Camera is being recommissioned. And then all of a sudden, May, M2 glass, April, M2 glass, May, LST Camera, June, M1M3 glass, first photon. That'll be pretty exciting. All right, let's kind of talk through that. You've seen these pictures. This was just reminding you that we've practiced a lot of the procedures for LST Cam arriving on the summit. Here's the schedule I showed you already. This is now M2 with surrogate and the baffle are being installed on the telescope. We're just taking the ComCam off now. That's only going to take us a month, but then we'll have that on the system until next year, February or so. And we can continue to test the M2 system in situ for that whole time. ComCam is off now and going back on in a month. And LST Cam's a few months out. And here is the M1M3 cell coming up on to the top of the to level 8 of the observatory. All right, so M1M3 cell in situ, that's starting in the middle of September. We have about 6 weeks. And here's the fun story. We hope to do all of those things in bullets in those 6 weeks, like make sure the system is safe for glass. Turns out that's an important requirement for moving forward. That's really a lot of the dynamic tests. We would like to also functionally test the M2 in situ. We'll get to that if we don't get to that in September, because it's on for a little while longer. We still have some verification and validation of the actual TMA performance. How well does it track on sky? Does it meet its requirements for slew time? All those things look like they're close, but we haven't actually had enough time to test them and create full verification reports, et cetera. So we'd like to do some of that. And then really this whole full system mechanical operation together. Could we pretend that we are on sky, drive the telescope on sky, between each fake exposure, adjust the shapes of the mirrors and all of the hexapods, and convince ourselves that we could do that should we actually have information from the sky on how to do that. And then of course, adding in simulated AOS images, for example, might be a nice thing to do, but it's only 6 weeks, maybe 7 weeks. So there's the mandatory and the nice. And here is my favorite question for this entire session. What would you do if you were in charge of this? I have a pretty good idea what we should do, but what would you do? Or really more importantly, what will you do? And how can you help? And the reason I'm asking that question is we have the team in place to get this thing done. And we have a team in place that can look at the data coming out of the system and say, that's going well. But where we're going to struggle is if we get to a place that, oh, this system's not quite performing as nice as we would like. What if somebody could really dig into the data? And imagine that you joined our phone con that's on Thursdays, Tuesdays. There's a day of the week where these things happen. And said, hey, I know how to make a plot. I could probably query a database. We'd love to have you. Then next is the M2 surrogates going on, so that the white surrogate here has to come off. And we'll be testing the M2 cell and surrogate on the TMA. The difference between the M2 and the M1M3 is the M2, we had a stand where we could take it through all its gravitational vectors and test it at all of those ways. For the M1M3 cell, we tested it at 2 angles, and we certainly never tested it at speed before we installed it on the telescope because there's just not a way to do it. Verify that it's meeting all of its requirements. After we take the M1M3 cell off to start putting the glass on and coating it, the telescope will have that yellow cross surrogate back on. We'll be back on sky, and really literally on sky. We don't have any mirrors, but we have 2 telescopes strapped to the side of our telescope that we can determine where the telescope is pointed on the sky. And so we'll be verifying the TMA performance using the star trackers. And with the exception of the M1M3 coming off after 6 weeks, the rest of the system stays on for several months, and we'll be going through lots of testing there. What would you do in this time? What will you do during this time? And could you help? Here's the commissioning camera. It's a still photo. You don't know if it's going on or off. It's going on. It's coming off today. Here's what it looks like on the telescope. We have deployable platforms, so you can walk out to the camera and fix stuff. So far, we haven't had to use that very much. Pretty much the commissioning camera has been a workhorse. And there's the M2 surrogate in the background. ComCam has been in situ for almost a year. ComCam will be in situ on the telescope for another 6-7 months. And we can't see the sky, but we can characterize CCD performance. We can do biases, flats, darks, and really determine a lot of things. We control this camera with the observatory control system. How can we continue developing control systems, make them better? They're already perfect, Thiago, you're good. What could you do with ComCam? What would you do with ComCam? How could you help us learn more about the sensors that use it in the Rubin Observatory, instrument signature removal, things like that? And the camera is going to go on an airplane. I think probably my favorite thing about my entire job for the last decade is that I could tell people, you are getting on the airplane with the camera. Turns out no one said no to me. I'm going to be in a hotel in Santiago waiting for it. You know, I'd like to see it land. I don't need to be on the airplane. The people on the airplane are really going to be fantastic. They've taken care of the camera so far. And we take very seriously the idea of moving a $168 million camera to a different continent. This is our mass simulator on the camera shipping stand. We've shipped that to Chile. I think you heard her in Aaron's talk. They decided to land in Brazil. And you might think, what's going on? Well, we're getting an extra takeoff and landing out of this deal. It was fantastic. For the Reil camera, it's a chartered flight. We're coming straight to Santiago. People ask, can you land in La Serena? Yes. Can you ever take off again? No. And so we have a few more months at SLAC, hopefully only a month or so more of electro-optical testing. You can imagine making yourself useful there. I know we have a lot of people in this room that have in fact been at SLAC helping the team. And while I'm giving blanket invitations to everyone in this room to come and help, we're of course going to have a conversation to make sure, you know, you actually can be helpful, all of those things. One of the questions that someone like me gets very often is, can I come to Chile and see it? Yes, if you dedicate at least 2 months of your life to helping me make it work. Tourists aren't quite high on my list quite yet. We get tourists, don't get me wrong, they're there. But could you help with this epic of the camera, the final epic? We have members of the telescope team. They're going to be at Slack helping pack stuff up. Most of the mechanical integrations, critical lifts, you're not invited to be part of that at all, right? Freddie Munoz is going to drive the crane. You cannot have a turn. But things like looking at data, looking at telemetry, trying to help us understand the system and make it better, there's opportunities there. And for those of you that already are part of an in-kind contribution, the paperwork is already done. So I'm talking to you. LST Camera arrives on Pachon. This is the truck with the camera shipping container with the camera fixture that holds the camera with a fake camera in the truck that landed in Brazil first and then came to Santiago, arriving at the very top of the summit. That's happening this calendar year. Can I say that? Good. This calendar year. And then when the camera arrives on Pachon, like I mentioned, we have to get it out of the way so we can start putting M1M3 glass together. It goes into the clean room, the white room on the summit, and we will re-verify it, make sure it's all working the way we want it to. That particular program, again, it's probably fair to say that there's a little bit of time pressure on us. We would like to be efficient in our re-verification of the camera so that we can get to the point of it's time to put the camera on the telescope. And so if you've been part of the camera team, if you know how to look at camera data, if that's something you already have experience with, what would you do during this time? How could you help? Oh, here's a picture of the camera in the white room. That's fun. We have about 3 or 4 months in the white room. There's always a balance of schedule. If you can re-verify the camera faster, then you can get it out of the clean room and onto the rotator, but only if you pull off ComCam first, but then you get started on upgrades. There's lots of balancing and things like that. That's the sort of thing that we do every day. How could we adjust the schedule to make it a little more efficient? Can we capture a week back safely, intelligently, and keep this thing moving along? Re-verification, if you know how to look at camera data, if you know how to look at CCD data, if you've already been part of that team, talk to that team. And then imagine April 2024. This is the M2 cell with a surrogate. It goes on the telescope. This is the commissioning camera surrogate. The real camera goes on the telescope. May. Here's the M1M3, but there's glass on there. It's coated, it's shiny, it's beautiful. June goes on the telescope. First photon, that's pretty exciting. Will you be ready to help? Are you interested in helping? Turns out that astronomers typically like images that are in focus. And I know how to do a focus scan, but you could probably do better than just that. And so we have an active optic system that we need to commission, and we have about 3 months to do that, to go from we've never had this system before to this is the most beautiful astronomical image ever taken by humankind. I mean it. Unprecedented, am I supposed to? No. 3 months, not a lot of time. There's going to be problems. We're going to have challenges. We're going to have questions. Some of you in the room have done this a few times. Some of you in the room have never seen anything like this before in your life. It's going to be fun for all of us. What would you do if photons were coming through the whole system and into the camera, producing data? How could you help during this time? And so I would love for us to hear from a couple of the people on the team that decided they could help. So you get a feel for what I'm talking about when I say, well, how could you help? Dominique or Peter, who's first? If you know how to make full screen, I do not. Why is full screen?
Okay. Okay, so yeah, as Kevin said, I joined this effort on M1M3 analysis two months ago, and in fact, I'm very very happy of this decision. So I'm going to explain, to try to give you an idea of the workflow of how we are working. So the idea here was an analysis on mirror positioning. So what we start is we start with a Jira ticket. So Jira is a project management system in order to keep track of all the action. So we start from a Jira ticket where the task is described and give you some information. And then you have some specification here. The mirror decenters at less than plus or minus 6 micrometers. Mirror tilt is less than plus or minus 24 10 to the minus 6 degrees. Piston, which is a motion in the z direction, is less than 1 micrometer. Okay, so then you try to find the data, the corresponding data, in order to make the analysis. You get time series dataset using the engineering facilities database, which is running a system called InfluxDB. So don't be afraid of that. In fact, it contains a number of topics, which are collection of actuators and sensor data, which all this information is documented. And then you have to access that through an API. So no need to build some complex queries. This is done automatically for you. And you get the results in a pandas data frame. So something very similar to what we do and what I am doing in Desk, for instance, to analyze some data. And then Merlin, who is extremely truly in that, provides a very convenient set of tools in order to simplify data retrieval. So we have everything. So for this study, we use a data set associated to TMA elevation slews. So the telescope, so the mount is moving from a given elevation to another one. We were able to find the right data set looking at the test log. Every night a log file which is written here, and you have all the details where you can find your data set. And then you make your notebook. And here is the result. So you have the mirror position in X, Y, Z, and the corresponding rotation in X, Y, and Z. And you have the position after when the slew is complete minus the position before the slew is complete as a function of the elevation difference. And you have, if you are looking at the Z position, for instance, you see that you have a nice linear dependency. And unfortunately, the specification, which is indicated by the yellow line, is you are completely out of spec. And by a large factor, because this is a factor of 70, you get 70 micron instead of plus or minus 1 micron. Okay, so you discuss this with colleagues, and you go to the Reil experts who take some time to think a little bit about that and said, that's very strange. And after some time, Doug said, mirror is expected to move in large slew. In fact, it's something which is normal, and it should be compensated by M2 camera automatic realignment tool using the lookup table. We should only be comparing the location of the M1M3 as defined by the IMS. IMS is some measurement system, position measurement system for the same elevation angles. Okay, so we implement that and we repeat the analysis for several slews ending at a given elevation angle. So for instance, you have slewing to 90 degrees, you are coming back to 44, 5, then you are moving to 0, back to 45, and you are comparing the mirror position at, say, 45-degree angle. And you see that it is much better. You are not yet at 1 micron, but the sigma is 5 microns. So we are much closer to the specs, but of course we have several things to understand, and especially the origin of outliers, which are not represented here. In fact, from time to time, your mirror position is totally off by millimeters. And at the moment, we don't really completely understand that. And during this analysis with Craig, for instance, we also discovered a couple of issues. We discovered that the sensor is not working correctly, and others are probably incorrectly read out. So we write a Jira ticket in order to declare that there is a problem, and someone will take care of that and will correct it. Okay, so that's it. And before giving the floor to Peter, I just would like to say that you can really contribute. That's something which is. This is not extremely complicated. You have to spend some time to understand the system, but this is data analysis. Data is data, so it can be cosmic shear data. It's mirror data, and this is extremely interesting because you really understand how this system is performing and how it works. Before doing that, I had a very naive idea of what is a M1M3. Basically, I thought it was a piece of glass on something. And now I realize this is something extremely sophisticated and extremely precise, and that requires a lot of work in order to make it work in the correct way and also not to break it.
Cool. So I wanted to highlight sort of a different mode of data analysis that we also get to engage in. So what Dominique was talking about was, we have a set of requirements and we sort of know ahead of time what are the things we need to validate with that. And so that was sort of a set of data analysis that we knew was coming up. The other sort of mode that I have been involved with and that I see kind of often is something comes up with what happened last night or what activities we were running, and we need someone to look at the data now. And so what I'm going to be talking about is a little bit of work we've done. So that was led by Freddie, but when we took off the yellow cross, the mass surrogate, and put on the mirror cell, we needed to rebalance the telescope. And we were finding that, so this plot that I'm showing here, the x-axis is the elevation of the telescope. The y-axis is the torque required as a function of elevation. And the color is green is for upward slews and purple is for downward slews. And so as you can see there, there's some weird discontinuity, and you can trust me that the values we were seeing for the torque are larger than we wanted, and there's some hysteresis, meaning that it wasn't centered around zero. And so we sort of needed someone to kind of go look and prepare all this telemetry data so that we could then send it off to the contractors to make sure, or to start opening communications with why it's behaving this way. And so sort of the workflow that I was engaging for this, so we have a tool called Coronagraph that helps visualize time series data. And so you can sort of initially jump in there and get a rough idea of what things look like using that. And then there's some tools that Merlin developed in a repo called Summit Utils that allow us to kind of query this EFD data to get the telemetry and create notebooks using that. And like I said, unlike the kind of the LVV test that Dominique was talking about, this was kind of reactive. But yeah, so basically what we were wondering is why there's this big discontinuity here. And here's kind of physically what was going on at that time. So on the left is an image of the TMA on the side of it. And you can sort of see there's this magnetic rail that feeds through the motors, which there's a zoom in on the right. And so on the right is when the telescope is pointed to zenith. And you can see that some of this magnetic rail is sticking out of the motors. So kind of this area right here, this is the magnetic rail. And so then what Freddie was able to find is that when we start pointing at 3.5 degrees, which is where we saw that discontinuity. So now on this left-hand picture here, the magnetic rail ends. And when we start pointing below that, there's part of these two these two metal pieces that the magnetic rail is going in between are E&M motors that are driving the elevation axis. So they're putting power in there and it's not acting on anything. And so that was kind of, so we were able to kind of find the cause of what's going on there. And so we were able to kind of mask out that region And so I'm showing the similar plot where, again, the green and purple lines are what we were seeing before with elevation versus torque. And then the blue and orange lines are showing if we mask out that region and go through our balancing algorithm and kind of create a new balance, that's what we end up with. And so this works much better. There's still some other issues that we're in contact with to kind of help figure things out. But I feel like this kind of shows an example of where it's useful to have someone who has some brain cycles that can make some plots that can kind of just speed along this form of communication. But it's definitely kind of a different mode of helping out than, you have a ticket that is coming up and you have a little longer to work on it. So yeah, so just to kind of summarize what we both said, that there's like a couple of different ways to get involved. There's some analysis tools and they're becoming easier to use, and Marilyn and others are helping us develop even more of them. And there's some tag up meetings, and if you want to kind of follow along with what we're doing with M1M3, I linked the Slack channel in there. That's all I got.
So I probably mentioned a few times that you could be helpful. And I don't want you to think that if you don't help, we won't get there. We will. But if you are helpful, maybe we get there a little sooner. That whole first photon thing, first light thing, I'm excited about that. And when everything works perfectly, you make a plot, everybody's happy. And when it doesn't, I mean, the one that Peter just showed, we pulled our hair out on that one for a while. And then you're like, oh, that's easy, that's simple. But it took an awful lot of people thinking about it. And our best engineers were like, I got no idea. And then it's just it's a feature. It's a feature. We can balance the telescope with this feature. It turns out that if we try to observe with the telescope at 3.2 degrees above elevation, I don't know what the air mass is. I've looked up the curves on the internet, and some of them say it's 0 air mass and some say it's infinite air mass. We're not going to observe down there, I promise. And so we wanted to spend the rest of the time just really giving you an opportunity to ask us questions. There's several of us here that have been doing this for a while. You can ask questions about, hey, next year looks fun, or tell me about this, or tell me about that, or hey, I love nothing more. When I have nothing else to do, I just think about making plots with Python. Love to talk to you. So there's a couple of microphones. If you have a question, you have a concern, you have a comment, please.
Kevin, I saw that your sequence for installation, I think it was M1, then camera, then anyways.
M2 camera, M1M3.
Camera, then M1M3. So is that for sure? Or what is?
It's a 2.7 sigma for sure.
Okay. Okay. All right, great.
So I'm going to give myself a chat GPT prompt. Act like an interested but inexperienced individual who's interested in helping Kevin and pose a question to him. Okay, imagine I'm sitting in the audience, I'm interested, but there's this entry barrier where people don't want to impose on you and your colleagues for hand-holding. There are a certain set of skills that you need, and there's a learning curve that people need to go up. So what is the most efficient way to engage in the way that you're asking?
I believe the correct term is the Vulcan mind meld. Short of that, we have got lots and lots of examples of how to do this. We have people that, so for example, we have, we have groups of people that love nothing more than to teach you how to use the Rubin science platform. We have groups of people and lots of example notebooks of how to do lots of different things. And so really it is just up to you to say, first of all, you need to have an account on Rubin, getting into a notebook. If you can get to a notebook, we should have the conversation after you can already open a notebook. But once you can open a notebook, there's just an enormous amount of examples of things that we've already done that you could play with and not break anything because it's not on the mountain. and just ask the questions, but really I think everybody knows that the learning curve to be part of a project like Rubin is enormous. And yeah, we don't have time to hold your hand and teach you. But what we have done is created an awful lot of examples of things that we had to do. So we did it. And now if you look at this, Peter, do you have lots of good comments in your code? Peter does. I'm just going to say, I don't know if he does. But if you get yourself as far as looking at an example notebook, someone can probably help you from there. And there's people that can actually help you get to open a notebook. But and then yeah, if you're comfortable at the point that you can open a Python notebook and create a plot using a random number generator, you're probably ready. We probably aren't going to give you we need this solved tomorrow morning at 8:42 a.m. We're not going to give you that problem. But we'll probably say, hey, here's something that we need to look at. And if you want to work on it for a couple of weeks, get back to us. Send.
So what we try to do too for M1M3 in particular is create groups of people of different levels of expertise and to work on one particular ticket. And that worked, I mean, I can say that worked well, right? I mean, I know Dominic, you didn't have a lot of experience, as you say, with M1M3. And that also helped both getting through a little bit of that learning curve, but not perfect, but it actually, I hope, helped.
I'll just add that a big part of working on these analyses is in the context of what's happening. So if you start coming to the working group of the people who are working on M1M3, listening to those conversations and understanding what's going on, that'll help you get to the point where you can understand enough to at least ask questions, because there's a lot of terminology and just basic understanding what's going on. So once you've talked to Kevin or whatever, and you've started to boot yourself up and you're sort of assigned to some project, you need to kind of spend the time of being with those people who are working on it week after week to understand what's happening.
And I know a lot of us are getting on airplanes soon, but maybe if the people that have been doing this already can turn around and face that way. All the people that are already doing this are sitting in the front, Craig and Tiago, and yeah, stand up, turn around, wave hi. Stay standing. You guys too.
Yeah,
I know you're all doing this.
Yeah, I'm Craig Lage. I've got a whole bunch of notebooks for analyzing different things here. So if you're interested, send me a Slack and I'll get you started.
Grab them right after the session and say, hey, I would love to help. And they'll say, oh, that's awesome.
Yeah, just a simple question. Out of curiosity, how many people are needed? Is this a dozen?
A dozen.
100? Oh, okay.
Yeah.
We can definitely use more than 5. We have a lot of topics open, and we need somebody to look on those.
Right. I mean, that number is kind of the balance of how much time do we have to help them learn and how much work do we have for them to do. How much work is 25? How much we can help people learn? 12.
Yeah, and we also take people in systems engineering. Like if you feel like verifying something, you would like to help us, you can also say here, hello here.
We don't draw boundary conditions.
No.
And I just mentioned that I have very, very strong feelings for the in-kind contributors that show up in Chile. But this is the sort of thing you can work on from home. And then I'll also have very strong HR appropriate feelings for your contributions. Oh, you can't leave the room until we have a drop of blood confirming that you are committed to this. Or a sign-up sheet, or send us a note on Slack, or yeah. Hipotéticamente. I can hear several of you whispering questions to each other back there. I could see you. I'm standing up here. So I'm really okay to answer your question. My battery's empty, but I'm okay. Undergrads, if they know Python, yeah, bring them. I was talking to you.
Yeah.
Yeah.
On the note of undergrads, it's a different account system, right? So like our undergrads, they use RSP a lot.
You are an in-kind contributor. Bring your students.
So yeah, so it's fairly straightforward to get them the same passwords and all this.
Someone has to fill out a form. That's me.
Okay.
Eli?
Eli.
I'm curious, how many forms do you fill out every day in general?
Not enough.
Oh.
Anybody else?
Keith, what's our global in-kind count? We're like 180 people.
Yeah, it's a little bit tricky to do the accounting because it involves, there's the international in-kind contributors that are working on commissioning. They have a commissioning contribution. There's a contributor to the US-Chile Announcement of Opportunity Program. And it's worth noting that some of the international contributors have been associated with the project for many years, right? And have been regular contributors. There's also a number of like institutional groups that have been contributing for many years. But if you add all those up, it's something like 200 people, okay? Of which maybe 100 of those people already had some kind of project connection, but probably about 100 people, you know, have been onboarded in the last year or so.
And for those
And
of you,
for those people who are already onboarded, it's even more straightforward, right? Because you should already have the accounts, and so we are asking for your help. This is an open call, particularly for the people who've already been onboarded, and there will be more calls like this over the next year.
yeah, and I was just going to mention it. Some of you are really looking forward to having images. Helping us with this stuff, we'll get those faster. So bring your skill set. And just so Kathy knows, I'm not going to bring the schedule forward by a month and a half, but a week, 2. Well,
Kevin and Holger are asking for help on the set side of things and the SVV side of things. If you think that sounds like fun, but my skill sets are better suited to figuring out photometric anomalies or whatever, there are opportunities to work there as well. So the same basic tools can be used for things closer to images. They can be used things closer to the hardware. We'll also take you if you'd like to come and sort out Auxtel data. So there's a very wide range of opportunities to come and do things on this project, all aiming towards first Photon in about a year's time. And the comments that Keith was making apply to those people. I mean, some of those people are on that further on that side. And the fact that Dominique currently ended up working on mirror problems rather than on astrometric problems on Auxtel is kind of a matter of choice. So you can choose where on that continuum you want to go, or indeed transition from one end to the other.
yeah, opportunities everywhere. Getting the system in focus, AOS opportunities, getting the telescope working opportunities, M1, M3, M2, LST Cam, ComCam, lots of opportunities.
Yeah, maybe a little comment. In fact, it should be clear that you don't need to be 100% working on the M1M2 analysis, of course. You can do several things. And I think I intend also to work on the astrometry part. That's not a problem. I have other responsibilities. And I mean, very frankly, for me, it's kind of a hobby. It's relaxing to working on system 1 and 2. Yeah. So no, I mean, if you can devote only maybe 25% of your time, less than that, I am not sure it's useful. But 25 to 30, 40% of your time, that's already a lot.
And it could be that long for a month and a half, and that's it. And that'll be still awesome. mean, assuming the learning curve and all of that is managed, but come in, come out, volunteer for this week, can't do it next week. Yeah, still like to chat. All right, Sandrine is guarding the door. She'll be taking names. Thank you for coming. We'll be, several of us will hang around and we'll be answering questions.